simplify some constraint optimization problems, we need to use a method called usually called the method of Lagrange multipliers, but in fact it is more KKT multipliers because Karush-Tucker conditions have generalized or extended Lagrange's method a little bit. But in any case, the topic of this episode, small subsection, is thanks to José Louis Lagrange, or many other names he went by because of his Italian heritage and then German work in Berlin and then retirement and work in France, and so he's widely considered French French mathematician or French engineer scientist. Has done a lot, including the method of Lagrange multipliers that we need for our next topic and for our progress. So in general form, if we have a problem that is specified in this constraint form, that the problem is, okay, minimize some function subject to some inequality constraint and some equality constraints. If we have a problem like that, then what Lagrange and others following after him have shown that you can rewrite this problem, constraint problem on the left, into a non-constrained version on the right, where you simply write a Lagrangian that includes your original variable, and you have new variables called Lagrange multipliers for each of the constraints. In this picture, in this formulation here, I have conveniently just named the greater than or equal to constraints with alpha. Those coefficients that correspond to the greater than or equal to constraint are named alpha sub I, each multiplier for each constraint. Lambdas are for less than or equal, and mu's are for the equality constraint. But in fact, you just have all of the constraints with a corresponding multiplier that is estimated now together. So we are optimizing now this whole Lagrangian, and we're minimizing it with respect to x, and that is because we're converting this problem, constraint minimization problem, into an unconstrained problem. We're minimizing with respect to x and maximizing with respect to our Lagrangian multipliers. So maximizing with respect to Lagrangian multipliers and minimizing with respect to x, and that gives us, ideally, that gives us a saddle point where they meet and we get our solution. One thing to watch out, so for example, and I'll explain in next slides. That when you are minimizing a function and you have a constraint to satisfy that some function of x should be greater than or equal to 0, then when you're minimizing and putting new constraints on the multipliers that they are non-negative, we'll treat mu in just a little bit. Then you put a negative sign here when you're minimizing a function and maximizing with respect to alphas. But when it is a less than or equal constraint, you put a plus sign. when you're maximizing, instead, you flip, this goes plus, this goes minus. And the trick here is that you can start thinking about this for equality constraint, which sign to put. But in fact, if you take mu out of the picture and allow it to be any sign, because it is an equality constraint, the optimization will sort it out itself. So necessarily optimality conditions. Once we took a constraint problem, three people at different times, which we will see at the next slide. Garouche in 1939, I believe, in his master thesis, and then later Kuhn and Tucker established that once you reformulated your problem in this way, your constraint satisfaction problem in this unconstrained way, for solution, it is necessary to just solve this system of equation when your gradient with respect to each of the gradient of the Lagrangian is zero with respect of your original variables and each of the new multipliers. So then when the conditions, this is a slide from Wikipedia, you can go and look it up and read a little more in detail. My goal here is to give you an intuition, not to derive everything, but we'll derive some stuff to gain the intuition. So basically what we're saying that the following condition needs to hold, or they will hold at the solution. So one thing to let me so one I'll show you a demo, but one thing to understand and look up in the slides. I've linked Christopher Bishop's book. A PDF is available online. Look up his Appendix E. He gives the following intuition. So if we have a constraint, let's have an equality constraint, right? So we want to maximize, in Bishop's example, maximize some function, and we want to have an equality constraint. So geometrically, it's say if we have some 3D function here, and then we have an ellipsoid. So we want to find a maximum of fx, which is this paraboloid here. But the maximum constraint to gx, so the maximum will be somewhere here. But the point is that the gradient with respect to gx is always perpendicular to that surface, to that, well, it's a line here in my drawing, in my example, but the gradient will be always perpendicular, and Bishop gives a nice intuition for that. So we know that g of x equals 0 for some x on this constraint. And if we take g of x plus some epsilon, such that this next step, x plus some epsilon, it's still on the constraint, there will still be 0. But now let's do the following. Let's do a Taylor expansion of g of x plus epsilon, which is nothing but g of x plus well, because we're dropping all of the other terms, it's approximately equal. But since those two are equal now, we now see that the gradient is orthogonal to that step along the constraint surface, or approximately orthogonal. If you let epsilon go to 0, the gradient becomes orthogonal, and basically gradient of g with respect to x is orthogonal to the surface that we're that we're using as a constraint. So when we're using an unconstrained Lagrangian form, and when we're doing this, it's another geometric intuition will help us. We're also justified because at the solution, wait, let me get my colors right. So my gradient with respect to g will still be pointing orthogonal to this ellipsoid, but my gradient with respect to f will be collinear or parallel to the gradient with respect to g, because if it's not at the solution, at the maximum, if it's not, then say if it's pointing a little bit sideways, then we will keep moving sideways. But when there is nowhere to move, that means they're pulling apart or in the same direction, depends. But that the Lagrangian multiplier will figure out the direction of the pull. Let's check an interactive demo how it will work for us. So continuing, look at this example where we have a function that we're optimizing, and this function is the surface, the intricate surface here on the screen. I'm rotating it for you. And the goal is to maximize with respect to this function. To maximize this function with respect to the x and y, but being constrained to this circle sort of projected onto this function, or an intersection with a cylinder. Pardon my delays. So, but notice the important point. Red is our gradient with respect to the constraint, with respect to the g. Our constraint is equality constraint of staying on the circle while optimizing with respect to that function. So if we move slightly or not so slightly, notice that gradient, the constraint is still orthogonal, and gradient of the function is pointing, now it's pointing upward because you want to get out of the saddle point of the, well, out into the saddle point. But since we don't want to end up here, we want to maximize the function. So our actual solution is somewhere here. Let's try to get there quickly. Yes. You see it's orange, which means it's getting hotter. And add the solution. They will be collinear. That's the gradient of the function is still pulling up, but that's as far as we can go in that direction while still staying on the constraint. And in this point, we can make our derivative, total derivative, both with respect to the function and the constraint, we can make, or total gradient, we can make it zero just by fiddling with the Lagrange multiplier, the coefficient that will make their length equal and signs opposite. Okay, another example, a similar example. This is unconstrained optimization. And if we start it, the point just follows the field, sort of the lines of the gradient, and converges. If we add a circle as a constraint, then our point is constrained to that circle. Um, yeah, but hopefully you get the point. Yeah, it starts there, and now the gradient leads it towards this attractor. When we, I guess, well, it's hard to say what is here minimizing or optimizing, but the point is that it by solving the Lagrangian, by multiplying the Lagrangian, or actually setting all of the gradients to zero and solving for it, we're getting to the solution without dealing with constraints or doing anything special about the constraints. So let's consider an example. Mhm. Very simple, so you can understand what Lagrange duality does for us, how it helps. We want to minimize, with respect to x, we want to minimize this function x squared such that x is greater than or equal to b. So when there is no constraint, we know that the optimal solution is here at zero. And if the constraint is negative, like here in example, we know that it it doesn't matter. The constraint doesn't change anything. We're still at zero. And when the constraint is positive, this is the minimum right at the constraint. So let's take this example and rewrite it in the Lagrangian form. So this is a constraint form. Minimize a function f of x equals x squared such that this constraint holds. Rearranging, we have the following constraint, inequality constraint, x minus b greater than or equal to 0. So we want to minimize this constraint, and it's an inequality constraint, so we can't just let Lagrangian optimization figure out the sign. So we set another constraint and simultaneously minimize for x and lambda. And since it's greater than or equal to the constraint, it's minus lambda x minus b. So when we're minimizing, when we're minimizing we want this part to be greater than 0, because if it is less than 0, then or greater than 0 or equal to 0, right? When this is less than 0, we will not minimize this to 0. We won't be able to, because we will always keep adding some extra value in this writing. When this part is less than 0, then Lagrangian cannot get to 0 with respect to x, um, because lambda alpha is positive, or non-negative rather. Well, if lambda is 0, if constraint doesn't matter, or x minus b is 0, if constraint is active, it's right on the uh, on the constraint. Well, the constraint is called active when lambda is greater than 0. So for for this case, so we're solving for we're minimizing for x and maximizing for lambda, but such that alpha such that alpha is greater than 0. And let's solve, like here, we don't know what b is. We don't care what b is. Can we just use KKT conditions and arrive at something sensible? So how do we do that? We just differentiate with respect to x, and we differentiate with respect to alpha. And of course, what are we differentiating? X squared minus alpha, x minus b. So with respect to x, what do we get? 2x minus lambda. And with respect to lambda, we get minus x plus b. And from here, well, set it to 0. From here, we know that lambda equals to x. Well, and from here, x equals b. So yes, okay, x equals lambda equals to b, but we know that we have this constraint, so we just write that's what lambda is, right? It cannot go negative. So once b becomes negative, uh, lambda is 0. Just optimize your f of x. Just find the optimum of your parabola. And uh, yeah, but when b is positive, then x equals to b, and that is your solution. So another way we could have written this, we could have written first that x equals lambda over 2, and then lambda would still be max over 2b 0, but then x would be max of b 0, right? Like this over here, and divide by 2. Okay, that's one problem. That by just unconstrained optimization, just setting derivatives to 0, we found our solution for all, well, our constant b was there as a parameter, so for all possible b's. But let's look at another example just to get the point firmly that you understand what we're doing here with Lagrange duality. So let's solve the problem of finding the largest area rectangle inside an ellipse. So that could be this, or could be that, or could be this, or could be, well, we could quickly kind of guess that the rectangles that ellipse does not, that are not inscribed into ellipse, probably not the largest ones, right? Although, well, yeah, I guess there is no point in making a rectangle like that. It's clearly will be smaller than if you just inscribe it. But what it is, which one is the solution? So let's write this as a constraint problem, right? First equation of ellipse is here with major axis A and B. Well, A goes from here to here, B goes from here to here, and in this, well, recall our PCA example, our PCA class lecture, and remember that those are major axes, and in those axes we can just represent all of the points of that ellipse, right, x and y. But then the area of the rectangle will be x times y, just 4 times, right, repeated here. So our constraint problem is maximize the area for x times y subject to within the ellipse or on the ellipse. Well, we can see it's an inequality constraint, but we already intuitively see that it must be on the ellipse, it must be equality. Well, but maybe not. Let's solve it, right? So then we write a Lagrangian where we maximize with respect to x and minimize with respect to lambda the function and the constraint. If like, what do we need to do? We need to just write a system. Well, it's with respect to x and y. A system of well, again, it's alpha. So used to lambda, it's usually lambda. Why did I use alpha? I don't know. Okay, I need to change it to lambda because that's what I will continue using when I describe it. So with respect to x, what is it for y? Minus 2 lambda a squared x. And with respect to y, it is 4x minus 2 lambda b squared y. And the same we can do with respect to lambda minus x squared minus y squared over b squared plus 1, and set everything to 0. And then we can flip the sign, doesn't matter. It's by multiplying. Well, let's solve it. I mean, I've already done it for us. I won't burden you with going through all of the details. Besides, maybe, yeah, we can just go through some to make sure that we're getting what we're getting. We can express y here, which will be minus lambda x over 2a squared. And when we plug that in, we'll get 4x minus 2 goes away, lambda square b square a square uh, x equals to 0. And from here, I see that lambda square is 4a square b square, and lambda is 2ab. And then, well, that's what we get. Oh, well, okay, so we found what did we find? Yes, we found what to set x and y in order to get, given a and b, the major axis of an ellipsoid, what to set x and y in order to maximize the area of a rectangle inside of the ellipsoid. Well, clearly it's on the ellipsoid. It's inscribed in it. Um, so interestingly, you don't have to evaluate for alphas in general, or for lambdas or for Lagrange multipliers. Okay, I see why alpha is there, because we are in the support vector machine lecture and we love alphas there. But it's just any Greek letter would do. So basically, lambda doesn't have to be evaluated, and you can just solve for your variables of interest x and y, and then it's called undetermined multiplier, for example. But okay, active constraint and an active constraint is another thing to remember. And main point is that using Lagrangian multipliers and KKT conditions, we can convert a constraint problem into a non-constraint problem. And again, as in this example, notice that we can either have this 0 and then there will not be any effect, or we can have lambda alpha 0 and then there will be no effect on the optimum um, of this factor. Okay.